All right. Let's see if this. Okay. I think I got it now. Can you see a tablet with some writing on it right now? Can you all hear me?
Yeah, I see your like notepad with your
That's it. Okay.
yeah,
Let's see
okay.
if I can get the chat up too. Uh, there's a chat. All right. So what I'm going to do now is first, any questions about anything we've covered to date at all? Nothing?
I don't got anything.
Hold on. I'm all right. So we did 378. Hold on for 1 second. I think it's 378. All right. So basically, we've done capacitance, we've done resistance. We haven't talked about boundary values problems or boundary conditions. Isn't that right, class?
Yeah.
All right. So in the book, and you can unmute yourself or put your video up. I don't know if it, let me see. Hold on for 1 second. Since I haven't used this extensively for a long time, and a lot of stuff has for some reason changed. And I don't know why. But I guess there's all sorts of updates I probably need to do. Okay. So in your book, I'm going to show you this. We're going to do boundary conditions next. These seem a bit irritating, but they're actually quite easy. This is on page 186 of Dr. Wentworth's book, and I'm just going to show you this. He talks about the boundary conditions. This focus has not been working all day today. I don't know why. I try everything. But you've got the book, right? Can y'all see this? I know y'all mute
Yeah,
yourself.
we can.
You
Yeah,
don't
you can
have.
kind of see it.
Yeah,
All right.
I can see it.
You've got a book. Just looking it up, open it to page 186, and you'll be able to see this. But I'm going to talk about the boundary conditions, and I'm going to do it here on this pad. They're not hard to understand, but I'm going to just do one thing, see if I can get this focus going. I've been having nothing but trouble with focusing this thing. This is my one attempt. It's a docking camera that I got a couple of years ago from our department. And come on. That camera won't work. Hmm. I don't know what's wrong with this thing. All right. Let me just try my best with what I got. Anyway, let me go ahead and try. Normally it'll do an auto update, but it doesn't anymore. So with boundary conditions, here's what it boils down to. There are two basic sets of boundary conditions that are generally true almost all the time. The first is, and this is for electrostatics, it's the tangent electric field is zero. So E tan 1 equals E tan 2. Gosh, that's horrible. Uh, I am desperately trying to get this thing to do it. An update. See if I shut that. This helps. Oh, that's the most unfocused picture I've seen in a long time. Can you at least see this right here?
Yeah, I can.
All right. So what does it actually mean? Well, if you have a boundary and there's region 1 and region 2 here, then if you take a look at the tangent value of the electric field. Now, the electric field's going to have, they're going to have streamlines. So try to understand this. If you actually tracked what are called streamlines of the electric field, and just for the record, these are things that they are basically in, if you took the path or take the electric field at every point in space, and you start at one point and just followed tail from the tail to the tip, tail to the tip, all the way around, this would be a streamline. Well, where it intersects this surface between region 1 and 2, there's going to be a tangent component. If you take the electric field and above, just slightly above here, and projected it onto the actual plane that separates region 1 and 2, the field just above would be equal to the field just below that. And that's coming out so loud. How can I do that? Tell you what, I may be able to do one thing here. If I give me a second, I'm going to just bear with me. It's going to go dark, but hang on. I think it is. It should go dark, but it didn't. Yeah. All right, let's try one more. All right, and that's really terrible. Now I'm going to try something where I get this camera back up. Just hoping it works because this is really unacceptably bad. Didn't work. Oh my gosh, this thing's horrible. All right, back to this. I'll see what I can do. Uh, no document camera. We're just going to work with it, guys. I'm sorry. All right, so I'll try to blow this up a little more. But in general, when they take a look at the tangent electric field, what they're talking about is the value of the electric field in the one region just above the intersection of the plane equal to the value in the electric field just below it. Y'all with me, class? I'm trying to make this simple. And the thing is, the tangent electric field on both sides is the same. The reason for it is pretty straightforward. You all can hear me, right? This is not the best video, but at least you can hear me.
Yeah, we can hear you.
All right, so let's assume we have two planar regions. Here's region 1 and here's region 2. You don't need to write this down. This is in your book and in Whitworth's book on page 186, 187, and 180. So this is region 1, this is region 2. If you make a little rectangle here, now we'll say this has a length L and a height H, and it's symmetric. Above is the same as below. We're going to let the distance H go to 0. So it's going to become just an infinitesimal distance between these two. And if you look at the integral of the E field, so I'll go clockwise or counterclockwise. So if you look at the integral of the E field, and this would be E in region 1 and E field in region 2, then you know that the integral of the E field around any closed loop, if it's an electrostatic problem, is equal to 0. Do you all remember that, class? We talked about potential energy and how.
Yeah.
And so if that's the case, if you look at this, now we're going to make H go to 0. So if you're integrating it along DL, you're only taking the component of the E field that's parallel. And the only way this integral can be true right here is if E1, which is going to be a value, you can take that dot, and you can just take it length L1. And then it would be, now when you go this way, it's going to be minus that. Doesn't matter from here to here, it'd be minus, or from here to here. Minus E2 dot L1 equals 0. And really, it's just saying that the E field above is the same as below, or otherwise, you wouldn't have 0 voltage around a closed loop if you made it. This video is not exactly helping me make that point, but I can do it in class. Do you all remember hearing that in physics class? The tangent electric field across any boundary is the same or not? Anybody hear it in physics or not?
Can you say that again?
The tangent electric field above a boundary is the same as the tangent electric field below it. Did you hear that in physics or not, class?
I did not personally.
I did.
You did?
I didn't.
Okay. Well, that's you. I don't know who, if they teach that. Usually they do, but that's a very important boundary condition. This is one of them. The tangent electric field in the first region is equal to the tangent electric field in the second. That's a real important condition. The second, I still don't understand why in the world this thing is so absolutely horrible. The second is that if the surface charge density equals 0, I like starting there. So if there's no surface charge density, and here's region 1 and here's region 2, then the normal component of the D field in region 1 will be equal to the normal component of the D field in region 2. That's going to be true. What that means is, how can that be that bad? if this changes anything. Oh, it did. Okay. Well, it looks like it did at least. All right. Got an idea. Hold on. Try something. See if this focuses. I found where the focus is on this thing. That's about as good as it's going to get, guys. So we'll start there. Anyway, what it really means is this. If you had, now just imagine this, and this is in Dr. Wentworth's book. And I'll show you where it is because this drawing hopefully will be better than mine. This is on page 188 at the top. You still see how he draws this little like tuna can above and below a surface, medium 1 and medium 2, or region 1, region 2. Y'all see that?
Yeah.
All right. Now, he says the integral of d dot ds, that's Gauss's law, over a closed region is 0. Try to appreciate that. If we allow this delta H2, delta H1 to go to 0, then the d field above the region, the flux would be going out, the integral of d dot ds has to be equal to the integral of d dot ds going down. Now, the actual d field, if there's a surface charge, would be pointing down. And I'm going to get to that in a second. But if there is no surface charge, then this d field has to equal this d field if there's no charge enclosed, because we know if there is no charge enclosed in a region, remember the integral of d dot ds over any closed region is equal to the charge enclosed by that region. And if the charge enclosed is 0, the integral of d dot ds above is the same as d dot ds below. And what that means is this is true. So if there is no surface charge density, this is true. And this is an important one. This is the most common assumption. Now, if there is a surface charge, and I'll try to draw that, I don't think I can do the proof in a way that's meaningful to you guys, but suppose there is a surface charge. And if I make my little pillbox here, if you can imagine that, and you got some delta H where the same amount is above and below, and you look at the integral of d dot ds over the closed surface, charge enclosed. Well, the charge enclosed would be rho s times the area, and be the area of that upper plate. Well, d dot ds above and below will have the same magnitude in terms it will be equal to the actual value of rho s times a. It will be equal to d above it times the surface area plus d below it over the surface area. Try to appreciate the fact, I'm not trying to make this hard, but I'm going to get right to what he says. So if you go ahead and you take the differential form of that, and he has this in equation 3.110 in the book on page 188. So it's equation 3.110. What you end up getting is this. You're going to get, and he does it with a univector. I'm going to get another piece of paper and I'll show you. I'm not really focused on this. This is like focusing on something that's not that important. But if you go ahead and do it, I want to try one last thing. See if this helps. Did that seem to sharpen it up at all? Or not?
Yeah, it did.
Let me try this. That's about as good as it's going to get. All right. So if you take a look at this, his is going to be, if you have a region, I'm going to make this real easy for you. If this is region 1 and this is region 2, and you have a unit vector. He calls it in his book A21. This is just a unit vector from region 2 to region 1. If you take A21 dotted with D normal 1 minus D normal 2, or D2, I should say D1 vector of D2, this is only going to be the normal component. What you end up is getting the surface charge density. When you see it applied, you'll see it won't be hard to understand. But what I plan on doing is showing you these laws applied. And this is going to be, I'll level with you. It's a little irritating. You don't know why you're doing it. This one becomes important only when you have a surface charge density that's not zero. And the only thing this really is the integral form of d dot ds over a closed surface equaling simply rho s ds integrated over that same surface. And that A21 is just a unit vector that Wentworth chose to use that form of it. So back to this. If we look at example 3.24, and this is on page 189, I'm just going to show you. So here, this is so bad. One last thing. Anyway, for this problem, 3-2.4, he says, I believe it's that bad. About as good as I can get. He's got a problem, and he says, does he give the E field? I'm sorry, let's do a drill problem. So he says, and drill 3.29, all right. Do you have books available to you guys? Can you see this? All right, it says for rho less than 2 meters, epsilon relative is 2. And he gives you E1 in that region. Then for rho greater than 2 meters, epsilon relative is equal to 3. And he wants E in region 2. So I'm going to draw this looking straight down the z-axis. And you'll see what I'm talking about. So here, and this is going to be drill 3.29. He has, I'm looking right down the z-axis to make it easy. Got a radius rho equal to 2 meters. And here, epsilon relative in region 1 is 2. And the E field in region 1 is given as 3A rho plus 6A phi plus 9AZ. And then outside there for rho greater than 2, epsilon relative is, so epsilon relative in region 2 is equal to 3. And he says determine E2. He wants E in region 2. Y'all follow me, class?
Yeah.
All right. The first thing is determine what's tangent and what's normal. So if you look at this right here, this z-axis is coming out of my paper. This is the radial axis. So if you look at this, what is the normal component? Do you all understand the term normal, by the way?
Would it be row in? Or sorry, a row,
That's right. Normal component is perpendicular to the surface. So for E1, E in region 1, the normal component, I'll call it E1 normal, would be 3A rho. You all with me?
Mm-hmm.
It's odd. I'm used to seeing people say or do something, but I guess I'll have to forego. Now, the actual tangent component of the E field in region 1 would be the remaining. So that would be 6A phi plus 9AZ. And you can imagine it. Just imagine a cylinder. The only thing that perforates a cylinder, if it's infinitely long, would be the radial normal vector. And the other two, Z and phi, are parallel to it. So that were tangent. Now, over here, we go to the law. We know that E tan 1, right, is equal to E tan in region 2. Y'all follow me on this, guys?
Yep.
We got E tan 1. That means we have E tan 2. It's 3A rho volts per meter. Done. I'm sorry. Sorry. E tan 1 is E tan 2. Sorry, guys. E tan 2. That means this is the tangent component of the electric field in region 2, which is 6A phi plus 9AZ. How can it be that bad? I'm going to try one thing. That doesn't work. I don't know. Who knows? Anyway, so that's the tangent component in region 2. So the normal component, now you got to get the normal component, there's no charge, right? So there's no surface charge. That means D normal 1 is D normal 2. So here's the E field that's normal in region 1. To get the D field in region 1, D field is what? It's the E field times what, guys?
Epsilon relative.
That's right, times epsilon naught, right? I mean, what we can do is, here is the E field normal in region 1. So the D field in region 1 would be equal to 3A rho, and then I have to multiply this by epsilon relative in region 1, which is 2, times epsilon naught is equal to the D normal field in region 2 that we don't know. But we know that epsilon relative in region 2 is 3, and it's going to be times D. It's really D rho in the second region. And this is going to be wait, we want the, hold it, I'm sorry. This is right here, the D field in normal in region 2. So that is D normal 2. They have to be the same. But the D field in region 2 can be equated to the E field in region 2. And I'm going to do that right here. So I'm trying to cram this in here. So D normal in region 2 would be equal to 3A rho times 2 times epsilon naught. And that's equal to the epsilon relative in region 2, which is 3 times epsilon naught. And it's times the E field, which we don't know. And that would be in the rho direction, region 2, a rho. So the epsilon naughts cancel, they always will. And that means the E field that's in the radial component or normal component in region 2 is going to be simply 2a rho. And that means the total E field would be, and I can put it right here, the total E field in region 2 would be equal to 2a rho plus 6a phi plus 9az. And I'm trying to do this in a way that you can at least follow as best as possible. Why would it be that bad, though? As good as it's going to get. Who knows? Anyway, are you all with me, class?
Yeah.
That's the answer I think he has. He has 2a rho plus 6a phi plus 9az. What about the next one? Want to try that? Just, give yourself a little something, a challenge, you might say. So the next problem is drill, and this is drill 330. So here he says a surface charge density, rho s is equal to 3 nanocoulombs per meter squared, exists on a surface y equals 0 for y from 0 to 3. So I got to draw this surface. So here, I'm trying to draw this in a way that's useful to see. If this is x, this is y, and this is z. So here's y equals 0. He's got this kind of a surface, an infinite surface. Y from 0 to 3. Epsilon relative. And for epsilon relative, and for y greater than 3, epsilon relative is 12. So let me do it from the side view. If this is the y-axis, we've got this infinite surface charge at y equals 0. Try to imagine that. Here's the y-axis, and this is at 0. And here's the surface charge. Then from 0 to 3, you got epsilon relative is 9. So this region from here to here has an epsilon relative equal to 9. Then beyond that, epsilon relative is equal to 12. It's hard to see this, but remember, if you have an infinite plane of charge, and I hope you remember this, if I just have an infinite plane of charge with rho s on it and assume it's infinite, then above and below the plane, the ground plane, I said that the E field was actually equal to rho s over 2 epsilon A normal. Do y'all remember that, class? Or no?
Yes. Yes.
All right. So if that's the case, the D field would be equal to simply rho s, and it's not going to be a function of epsilon over 2 A normal. Y'all follow me? Just get rid of epsilon. Now, if that's the case, then if you look here, he's got this charge, infinite charge. It's really in the zx axis, infinite in z and x at y equals 0. And he gives us the value. That means if I look at this thing, and I'm going to flip it here, and I'm going to just make it a planar sight so you can better appreciate this, hopefully. So here is rho s, and this is going to be the y direction. Now, I know the D field below it is just in the opposite, it's downward in the minus AY direction. It's simply rho s over 2 A normal. And in this case, there'd be a minus. This one would be AY. Above it, the D field, D normal would be equal to rho s over 2 AY. It will not be a function of epsilon above or below because the charge is there. Do you all follow me, class?
Yep.
All right. Now, to get the value of the E field, now that we have the E field is simply going to be equal to the D field divided by epsilon in those regions. So the E field, if we take it from y greater than 0, less than 3, this is the region just after that surface where the charge is. The D field itself, the E field itself will be equal to the D field, which is going to be rho s over 2. And then you've got to take that and divide it by epsilon. And there, what is it? The epsilon value is 9, right? From 0 to 3. So it's divided by 9 epsilon naught. I'll just finish this one. So that means the E field between these regions, between 0 to 3, man, this is a pain looking at that. The E field itself would be equal to rho s, which is 3 times 10 to the minus 9. It's 3 times 10 to the minus 3 nanocoulombs per meter squared. It's going to be that divided by 2. And then it's divided by 9 and epsilon naught. You might as well make it as 1 over 36 pi times 10 to the minus 9th. I think that's what Wentworth wants in the AY direction. So that's going to be what? E in this region between y greater than 0, less than 3 is going to be equal to the 10 to the minus 9s cancel. And what do we get? You got 3 halves. I'll write it down. 3 halves. And then you got 36 pi over 9. So let's see. 3, 18, right? I think that's right. Did you lose access to OneNote? Someone?
Yeah,
And
so I tried going onto it like a few minutes ago, and it just says like I don't have access to it anymore.
does anybody else have that problem? I'll give you access right now.
I still have access.
Hold on. Let me, I can give you access to this in a second. I don't know. You did before, right?
Yeah, I was able to access before, but then I tried today and it just wasn't working.
Hold on. Let me make sure you can get it. This is weird. This whole thing's messed up. Give me 1 second. I'll get this to you. All right, I'm just going to forward this to you. This should work. Andrew Strickland, right?
Yeah.
Try this. That should do it. I'm sorry about that. I don't know what happened. I'm having problems. Unless they've done it, some kind of an update that I'm not aware of. All right, back to this thing. Let me see if this works because I have.
Yeah, that worked. Thank you.
Sure. I think that was the same old one. So for this, I have I think I did that wrong. Hold on. I got rho S is equal to 3. So Let me do it over here so you can see what I'm up to. This screen will be clear, I hope. Are you guys seeing something with MathCAD on it or not?
Yeah, I am.
Yeah.
So this is wrong here, I think. Let me go ahead and do this. So we got rho S, and I'm going to do it right now. Rho S is equal to 3 times 10 to the minus 9. I'm going to do the whole thing. That means the D field and the regions, regardless of where they are rho S over 2. And that's the D field. Now the E field in region 1 this is going to be for between 0 and 3 meters. Should be D divided by epsilon relative times epsilon naught. And I'm going to go ahead and put the epsilon relative. We'll call epsilon relative 1 here. So now he has twice that, he didn't account for what's below the surface. If you look this, if you take 2 times E1, that's what he got for E1. The problem is he didn't account for the fact unless now, see, the thing is, he could assume it's a perfect conductor and then he would be right. He didn't. He says exists at the surface y equals 0. That's usually just a flat plane. But if it's a conductor there and it's all like conducting below it, then you could just say it's rho S over epsilon would be the D field. But I was assuming it was just a sheet of things. What he's doing is assuming that value of rho S is not just the sheet period. It's got below there. I was assuming it was free space, but he didn't qualify that. He's assuming a perfect conductor. So his answers in there are twice what mine will be. But y'all follow me what I'm doing, class?
Yeah.
So I would make it clear. And again, I might as well make this clear to you right now that if let me try to do this. I stop the share stuff. I come here and now this is important. So just bear with me. I'll try to make it as clear as I can. If you have a perfect conductor, so put down conductor. Perfect conductor means the D field inside equals the E field inside equals 0. Do y'all follow me, class?
Yep.
Think of a solid piece of iron. Then if you have a surface charge density right here, then the D field above here This would be a D above. The normal component of the D field will just be rho S. But if you have a thin sheet of charge, this would be a sheet of charge. Then the D field above will be equal in magnitude to the D field below, and that would simply be rho S over 2. And this would be rho S over 2, and it would be in the A normal component. This one would be up, this one would be down. Y'all with me, class? Everybody's muted, but I mean, do you follow me on what I'm talking about here?
Why?
All right, well, you know the integral of D dot ds is equal to closed integral is charge enclosed, right?
Yes.
All right, make a little pill box, you know, one of these, like a Copenhagen, you know, the tobacco things, container, and make sure it's centered on the axis there. So the D field above and the D field below would be the same magnitude, right?
Yes.
Remember, it's a charge density. So if we take a look at what this means, the integral of D dot ds is the charge. Since the D field above is the same magnitude and up, D field below is same magnitude and down, but the surface vector is down as well. You get 2 times D normal times the area. That would be the area of this surface. And you can assume this height is 0, would be the charge enclosed. Well, the charge enclosed would be rho S times A. Do you agree with that?
Yes.
That would be this. So you can get rid of A, and you can see D normal in magnitude is just rho S over 2. That's why. Now, if it's a perfect conductor, if there's nothing down here, no D field, then the integral of the flux is all the integral of D dot ds only exists above it, not below it. So therefore, the D field would be rho S. That's the whole.
Because then we get D and A equals rho S A, and the A is canceled. So
exactly. By the way, he should have been more clear about that, because I thought it was just a strip with that charge on it, but he was assuming there's a perfect conductor below the behind there. All right. We'll do some problems with this with D normal and E. I want to just do the Laplacians now. And I think I got about 17 minutes or so. So this is the boundary value section in his book. It's on page 190. Okay. Let me see if I can make it clear. Probably not. I still don't know what happened to this camera, but I wish I did. So this is the boundary value part of it. It's not hard to understand this. What you end up doing is first starting with divergence of D is equal to the volume charge density. What's the name of that law?
Is that Poisson? Oh no, that's Gauss's. That's Gauss's. Sorry.
That's my favorite man, Gauss's law. This is the differential form. The integral form of that is the integral of D dot ds is equal to the charge enclosed by the surface. But I'm not going to worry about this. This is the one we want. Now, D is equal to epsilon E. You all agree with that? You all with me on this, guys?
Yeah.
So if that's the case, then divergence of epsilon E is equal to rho V, or I can say that if assuming epsilon's not a function of position, I can say divergence of E is equal to rho V, right? Divided by epsilon. Follow me? We're assuming epsilon's a constant. You okay with that, everyone?
Yep.
All right, then after that, and for electrostatics, E is equal to minus the gradient of the voltage. Y'all remember that?
Mm-hmm.
So plug that in here and you get divergence of minus the gradient of the voltage is equal to rho v over epsilon. Well, the minus sign can come up and the gradient, the divergence of a gradient is actually the definition of del squared. So divergence of the gradient of a vector is simply del squared of that vector v. So what it comes down to is this right here becomes simply del squared of v is equal to minus rho v over epsilon. And that is really called Poisson's equation. Laplace's equation is when it equals zero. It's the charge density is zero. Everybody okay with that?
Mm-hmm.
Next, the next thing we do is next thing we do is we see how it applies. So in Cartesian coordinates, so in the back of your book, I hope you all have your books. This is important. So if you look in the back of your books, the very last thing on that cover I can't get any better than that. All right. If you look at your cover, you're going to see the del squared operator for both Cartesian, cylindrical, and spherical. Can you all see that, class?
Yeah.
The only thing you're doing is solving these differential equations for the appropriate problem statement. And the easiest way to see this is just go and do a couple of them. And let's see what he's got here. First one's trivial. Let's look at example 3.26 on page 193. So I'll try to do this in a way that's meaningful. So here, this is example 3.26. He says, determine the electric potential in a dielectric region between a pair of concentric spheres that have a potential difference VAB as shown in figure 5.3. And really what he's saying is there, he shows you got some inner radius A, some outer radius B. These are spherical. Like so. And he's saying the difference between the two, this would have some VA, this is some VB. You all with me, class? You all still there? I can't even see who's here.
Yeah.
All right, good. All right, here's your chat. So I can see your chat. Okay, so we start, y'all agree it's in spherical coordinates, right?
Yeah.
You can unmute yourself. I don't care if there's background noise. So that means del squared of V, it's normally minus rho V over epsilon, right? But in between these two conductors, it's zero because there is no volume charge density between the two. So now we have del squared of V is equal to zero. It's in spherical coordinates, right? Yep. All right. So now I'm going to flip this and show you something. You can almost tell the way it's going to go. Here's spherical coordinates. The one thing you'll notice is if it's spherically symmetric, you got to just recognize that. Do y'all agree with that?
Yeah.
That means dv d theta and dv d phi are 0, or these two terms go away. This is the only term you have, the first one. All right, I'm going to rewrite that. So what you end up with is this. You have 1 over r squared times the first derivative with respect to r of r squared times dv dr. And this is a v, is equal to 0 because the charge density is 0. Y'all with me? Just repeat the obvious. All right. Now multiply both sides by r squared. It just gets rid of this because there's a 0 here. Now, if there was a volume charge density, it wasn't 0, it wouldn't be a 0. Y'all with me?
Mm-hmm.
Now multiply both sides by dr. And I get this. Think of it like dx or something. Y'all with me?
Mm-hmm.
Now, if you take a look at this is a differential, this d of this. So if you integrate both sides, now I get r squared dv dr here. And that's equal to simply, when I integrate dr here, I get r, but you see, this is an indefinite integral, so you're going to get really r plus a constant c1, right?
Mm-hmm.
Let me just write that down. It's r plus c1, because there's no limits to this integration. Everybody agree with that?
Mm-hmm.
Now, if I divide by r squared, and actually this should actually be a constant too. I'll call that c2r. Hold it. When I integrate this, pardon me, I end up getting just r plus a constant. Sorry, I'll call it c1. Now I divide it by r squared, and I get dv dr is equal to 1 over r plus c1 over
R squared.
r squared as such. Hold on for 1 second. Let me redo this. It's for his, the way he does it, he has one. I'm going to start it again. 1 over r squared, because I messed this up, I think, times ddr, r squared times dv dr, and that's equal to 0. I'm sorry. Now multiply that. It's still 0. Now that's 0 integrated dr. My bad. Now this is a complete differential. So when I go ahead and do this, see, if I integrate, it's 0 times dr here. If you integrate that, you still get 0 plus a constant is equal to r squared dv dr. So that means dv dr is equal to c over r squared. And when I integrate this side again, call it c1, and integrate both sides, now I get v of r is equal to c1 minus c1 over r plus c2. I'm sorry about that. That's 0 dv. 0 integrating dr is still going to give me 0, and it's a complete differential, so I have to take that plus a constant. All right, back to this thing. Are you all with me on this, class? If you take simply this right here, set it equal to 0 and solve it, you end up with that because it's set to 0 on that side. And if you look at this right here, I know that V when R is equal to A would be VA, and that would be equal to minus C1 over A plus C2. And when it's equal to B, VB is equal to minus C1 over B plus C2. Y'all follow me what I'm doing here, class? You guys still there? Can you guys hear me or not? Oh gosh, did I mute you?
Yeah, you're good. I was just
Oh.
writing that down. Sorry.
I mean, sometimes I don't know if you're there or not. Okay, y'all follow me on this? We got two equations and two unknowns. Now, if you look at this, if you take VA minus VB right here, so I got VA minus VB, I would have minus C1 over A plus C2 minus the quantity minus C1 over B plus C2. And you can see that the C2s cancel. So I have VAB, which is VA minus VB, is going to be equal to minus C1 plus sorry, it's equal to C1, there's C1, that would be positive. So it'd be, let me do it this way, C1, and it's going to be over B minus C1 over A. So I can say that C1 times 1 over B minus 1 over A, I'm assuming B is larger, is equal to VBA, or C1 itself would be equal.
Can you size your page up just there?
Yeah. C1 itself is going to be equal to simply VAB over 1 over B minus 1 over A. When you take this and plug it into this equation right there for C1, I'm sorry, this equation, you're going to get V of R is equal to VAB, and it's 1 over B minus 1 over A, and then it's divided by R, so it's 1 over R plus C2. Now, C2 can be anything because he didn't say where the zero reference is, so you can make that 0. Because remember, he only gave us a potential difference between points A and B. And if you look, this will work. So this is the V of R that we should get. And when you look at this, when R itself, right here, goes to A, goes to B, you're going to get 1 minus B over A times VAB. This will be the right potential. And let me do one other thing too, because in his book, I want to, oh boy. Let me just check this. In his equation, he uses A and B, but this is the equation he gets. Y'all see it, class? I hope you can see it. This is, he has minus A over R plus B. It doesn't matter if A is plus or minus because that's V of R. And then when he goes ahead and there's a slightly different variation on it than I do. Just take a look at this thing for 1 second. So here's DDR, R squared dVdr. That's right, equals 0. Integrate both sides. That's right, you get R squared dVdr. is equal to some constant. He chooses it as A. dV dr is equal to A over R squared. Integrate both sides again. Integrate that dr. We get V of R is equal to R plus second constant B. That's how he does it. And from that point on, he has a little different form, but he has basically the same form that we do. Are you with me on this, class?
Yeah.
All right, Hayden, I'm sorry that this is not working out the way I'd like. I think I'm about done, but I'm going to go through electrostatic energy and stuff next time. And when's our test, guys?
I think right now it's scheduled to be next class, which is next Wednesday, a week from today.
All right, you guys ready for a wrap up?
Sure.
Can you hear me? Okay? I'm not sure. Since the test is coming up, this material will not be on it. Y'all hear me?
What material? Just the boundary stuff, like boundary
Condition
conditions.
and the tangent electric field business isn't going to be on it, but resistance, capacitance, the electric field. I mean, generally, D field, Gauss's law, force, the transmission lines, and somebody should ask how many problems. There'll be about 4 problems, but each problem is a multiple part. If you look online, you'll see tons of my old tests and stuff like this, or you can go to IEEE's, that 80 Kappa News site. Basically, the way I make up my tests, and I try to be as clear about this as possible, I look at what homework I've assigned and what quizzes I've done and what I've discussed and make it up. Primarily the homework I would focus at. Y'all follow me?
Yeah.
Now, are there any questions relating to anything before this lecture today? I mean, I'll admit this is not exactly the ideal circumstance. I'm so sorry about this camera. I am going to do my best to get it better. But any questions at all? Hayden, Andrew, Zachary, Jonathan, Jackson, or Jackson, and Ming Lee, anything at all?
Yeah. So the test is going to be over all of what we've gone over, chapter 1, 2, and 3, and it's going to be everything up until the boundary stuff. We're not going to do that.
Electric fields, that's right. Today's
Okay.
like, think about it. One problem could cover resistor and capacitor, right? I do that oftentimes. Another problem would be like on transmission line impedance matching, series or shunt, right? Remember? And by the way, bring Smith charts. Bring the kind of Smith charts you want, put your name on them. I can supply you Smith charts, but if you found some you like, I prefer you use yours. Everybody with me on that?
Yeah, I still have a bunch of the extra ones that you gave me. I'll bring those.
Well, you can make, there's bigger ones available to you.
Okay.
And the other thing is, we've done bounce diagrams. Let's see, we've done the electric field, we've done force, the D field, Gauss's law problems, we've done resistance problems. But that's basically it. Go through the homework. Anything you don't feel you're confident about, review. It shouldn't, nothing's a surprise on this. Just you can look at my old tests and but really look at the homework. That's what I tell everybody. Because sometimes people say it didn't look at all like the old tests. I try to tell them it's based on the homework, not the tests. And here's why, because sometimes the class wants the test later or earlier. So there's different material and different classes of problems, but that's really it. Any other questions or any other comments? Nothing at all. Well, listen, I apologize for this camera being so lousy, but I hope I at least got some of the points across that were in the text. And next time we'll meet in person, okay?
Sounds good.
That was good.
Anything else? If you got questions, go ahead. I'm here online. Nothing? All right, if you need to talk or do something, just send me an email and I'll try to set something up with Zoom or over the phone or whatever. And now I'm going to try to fix that camera. And next Wednesday, we got a test, okay?